So now that you know a little bit about safe publication in terms of what the issue is, let's talk about some techniques that Java supports in order to enable multiple threads to share objects safely. So in order to publish a properly constructed object, in other words, one who doesn't have the this reference leak out during the construction process, in order to have a safe access or safe published, properly constructed object, two things have to happen. You have to have the reference to the object and the state of the object be made visible to other threads at the same time. They both have to be. It doesn't do any good to have one of them visible and the other one not visible, because then you'll be able to get access to the object but not its state, which would be really weird, but actually quite possible. So let's talk about a couple different ways to accomplish this. The easiest way to do this by far is to simply use locks, either a reentrant lock or the intrinsic lock that comes with a Java monitor object that you can synchronize on with synchronized statements or synchronized methods. That's sort of the no-brainer way of doing things. If you use that, you're done. So here's a very simple example. Let's say we're trying to implement a thread-safe singleton. So without going into all the details of what a thread-safe singleton is or what a singleton is, I assume you know what a singleton is by this point. We have an instance method, and what we're going to do here is we're going to synchronize on the singleton class's instances intrinsic lock. So this whole region of code is synchronized, which means when you go into it, it'll make sure the caches are up to date. It'll do its thing. It'll create a new instance of the singleton, and it'll return that instance, and then it'll push out that change to all the other threads. That's just the very nature of synchronized statements and synchronized methods. You could equivalently use a Java reentrant lock here. You get the same effect. Okay, so far so good. But what's the downside with this approach, especially in the context of a singleton? Why would we not just want to use this code all the time? So the problem using this code all the time with a singleton is we always acquire the lock, but we only really need to acquire the lock on the first time in. Because all the other times, we've already got this done, and so there's no need of having to acquire the synchronizer at this level. So this is too much synchronization. If you think about sort of Goldilocks, right? You've got too much synchronization. You've got too little synchronization. You've got just the right amount of synchronization. So this approach has too much synchronization. There's another way of being able to do this. This is more esoteric, but it does in fact work. And what you do is you initialize the object reference from a static initializer. So here's our singleton class, which has a private constructor, and it's got a public singleton method. And what it does is it creates a private static class called lazyHolder. And you can see that lazyHolder will make a new singleton instance, which is static and final. So this guy will actually be initialized, guaranteed to be initialized when the class is loaded by the Java execution environment, the JVM, for example. And therefore, when the instance method is called here, this has already been created, so we're done. There's one problem with this approach. What's the problem with this approach? It's always created, right? So now we're creating it all the time. But I guess in some sense, when we access it, it's loaded. So anyway, it's always being created. There's yet another way to do things. And this is a way that I had a hand in helping to add to Java, which is kind of cool. So what this does is this is going to store a reference to an object in a volatile variable using the right incantations on the right version of Java. You can read more about this here. So what we're going to do here is we're going to define a static volatile field. And by saying volatile, magic will happen properly if you use the right version of Java. You have to use Java 1.5 or later, which most people are using these days. And if you want to learn more about this, take a look at this link. It's the double-check locking pattern, which I created back 25 years ago or so. And what was interesting about double-check locking is it forced people to think very carefully about these memory management issues in Java, these memory model issues in Java. And so it touched off a firestorm of discussion, which eventually ended up having people in the Java community adding these capabilities to Java 1.5. So what happens here is the first time in result will be null. So we only acquire the lock on the first time in. So if the result is null, then we acquire the lock. Notice what we had done before here. We'd always acquired the lock whenever we came into the instance method. Now we only acquire the lock if the result is null. If the result is null, we acquire the lock, and then we check to see if the result is still null. So this is the double check part, right? So we check it here, that's the first check, and here is the second check. And so this then performs a lazy initialization, so it only does this on the first time in. So going back to William's point, the other example always created the instance. This one will do it only the first time it's called. So that's the double check, and this will work fine, and because of the magic of Volatile. And the use of Volatile in this context, in this particular idiom, avoids problems with partially constructed objects. So the problem that we would have had if we didn't use this trick would be that the reference might be up to date, but the contents might not be up to date because they would be pushed through the memory system at different times. So using this will ensure that we end up with a consistent result. And then when we're all done, we will go ahead and return the singleton result. And you can see here, either it had already been pre-initialized the first time in which case we're just returning it, or it was the first time in, we initialize it, and then we return that result. So that's the double-checked locking optimization pattern implemented using volatiles correctly in Java with 1.5 or later. Here's another way to do this thing. This uses an atomic reference. This is also a valid way of getting the behavior. Those of you who did the grad version of assignment 1B remember atomic reference, and I think I talked about it when I went through the code. So this approach will start out by creating an atomic reference that's null. And here's the instance singleton, and that should be static. It should be public static singleton. And this probably should also be static. And so what it's going to do here is we come in, the first thing we do is we get the value of inst, which as you can see starts out to be null. And if we get a null, that means this is the first time in. In this case, we go ahead and create a new singleton, and then we do an atomic compare and swap of this new singleton with null. And if you recall, what compare and swap does is it says, if the value of minst is currently null, atomically swap it, and then push it all out through the memory hierarchy so everything's safely published. If it's not null, then it's already been initialized, so we just ignore it. So if it in fact was null, if the comparison works, we've already got things set properly. If the comparison doesn't work, then that means that we need to go and get the value of this thing, which now should actually be the right value. So if this fails, we get the value of that. And in any case, we return the singleton that is either initialized or not. OK, so it works with respect to pushing the information out and publishing it correctly. What's wrong with this code? It's very subtle. The problem with this code is if things align, if the stars don't align properly, you could actually have multiple singletons created. And that's because multiple threads might come through at the same time, discover that nothing had been initialized yet, and then multiple threads would create the new singleton. Now, only one of them will end up succeeding in this compare and swap or compare and set call. But you have to make sure that the constructor of singleton can be called multiple times without having harmful side effects. So that's the main issue there. So this is also not a perfect solution. I think the perfect solution here is to use the double-checked locking optimization technique with Volatile. That's the one that's the best. And that's the one I helped to create, so of course it's the best. William. Yeah. Yes, so the question is this pattern used elsewhere? Absolutely, lots of things use this. It's a very common technique. The double-checked locking optimization pattern is very common, especially at in systems code, where the first time in you do something, and all the other times you just use what you did the first time in. So yes, it's a very common thing. When they do it in Linux or more at a C system level, typically they will use assembly language instructions that do what Volatile does at the virtual machine level. So you still have to make sure you put the right instructions in your code, but it would be done at a lower level. But yes, absolutely, it's not just limited to double-check locking in Java for sure. Okay, the fourth example we're going to look at here, the fourth way of doing things, is a little different, and so I don't use the singleton as an example because it's kind of subtle. So it's storing a reference to an object into a final field. And this is yet another way of doing things. And this is actually a very common technique, and you'll see in a second why we can't use it for singleton, sadly, but it does work for lots of other stuff. So you can see here we have class A with a couple of fields, M not final and M final. So M final is a final field, as the name suggests. M not final is not a final field. So let's take a look. If we were to create a new instance of class A in one thread, and then try to access its fields in another thread, what would be likely to happen? Keeping in mind that this is all somewhat subject to various obscure things. So what we're talking about is the guarantees versus what might happen to happen, what might happen by chance in some environments because the gamma rays struck the processors in some funny location or at some funny time. So if we try to access the not final field in thread 2 that was set in thread 1, that's not guaranteed to have any sensible value because there's nothing to cause it to be pushed out because it wasn't final. Whoops. Conversely, I should say, if you try to access the final field, it will be there because it was defined as final. Now, the interesting thing about this is there's actually a whole approach to concurrency and thread safety in Java that are called immutable objects. And immutable objects, as the name implies, are objects that once they're constructed can never change. So they are read-only after they're created. After the constructor runs, they're read-only. And that may seem a little bit obscure, but it turns out that you're very familiar with one of the most common immutable objects, which is class string. So if you take a look at Java's class string, you'll see that class string is defined to only have final fields, like value, and only has accessor methods. There's no mutator methods in string at all. And if you do operations that appear to be mutating, like substring or whatever, substir, it actually makes a brand new string. So once a string is created, it never can be changed. And you can read why they did that here in this article if you're so interested. So that's an example of something that has that property. So the bottom line here is that if you define something to be final, then it will be guaranteed to be propagated because it's read-only. Whereas if it's not final, then you have to do something else with it. But there's yet another little weird thing to keep in mind here, which is you could have a final field that refers to an object that's mutable. So in this case over here, where we had, long, once it's final and you set it, it's not changing, right? But what if we have something more interesting? What if we have something like a final field that's an array, right? So let's say we're going to have a string that's going to keep track of names of famous quarterbacks. That's not guaranteed to work unless you synchronize the access to the contents of that field, not just the field itself. So in particular, if we were to create a new object somehow, like we do here, the QB's field is final. You can't change that. But the contents of the QB's field, which is an array, can be changed. So down here, we could, if we wanted to change, QB sub 1 from Brett Favre to Peyton Manning or to Joe Montana or whoever, pick your favorite quarterback from whatever era. This has to be synchronized. Otherwise, there's no guarantee that the contents will be accessible, which is a little bit weird. And the same thing holds if you have a final field that's just a good old Java object. The field could be final, meaning that we can't change the object once it's been allocated, but the contents of the object would need to be protected. Now again, by far the easiest way to deal with this stuff is just to use synchronizers properly, and then the whole problem goes away. But when people try to get cute and they try to get clever and they try to do things like our singleton stuff that we looked at over here with the double check locking optimization, we're trying to be cute, right? We're trying not to have to lock every time in. And if you start trying to get cute, you really, really, really need to understand these semantics of safe publication techniques, because otherwise you're going to get yourself in trouble. So the thing to remember is to avoid all these headaches, just use synchronizers, just use readtriplock, just use synchronized statements and methods, and all the problems go away. But if you start getting cute, then you've got to really learn all these rather obscure characteristics and features of safe publication. Okay, so that's the end of that section.